Now, in this video, I want to talk about a couple of language features that are important to interprocedural static analysis and what are ways of addressing some of these challenges that these features involve in practice. So one of these features is recursion, right? So whenever I read a program analysis paper and it doesn't say anything about recursion, depending on the analysis, at least I get somewhat dubious and think about, okay, how could it work there? Because the challenge is here the following. I told you previously that in order to obtain a context-sensitive analysis that only walks along realizable program paths, we must somehow make sure that we keep track of the call stack, right? So we somehow must model this principle of matching returns against the appropriate calls. But because our static analysis domain also must be finite, or at least it mustn't have any infinite ascending chains, like you already learned earlier, we also know that we must somehow bound the computation and these contexts that originate from it. And that's at the very least true when the problem is not distributive. So as I will be showing you in a couple of weeks, when you have a distributive set of flow functions, so you have a distributive analysis problem, you can actually deal with recursion very nicely. You can basically compute a precise result despite recursion. That has to do with the fact that in a distributive problem, the MFP solution is just the same as the MOP solution. So the MOP solution is computable. And it doesn't matter whether you merge before or after function application. Therefore, you get there a precise result nonetheless. But in basically all other cases, you must somehow bound your computation, and there are going to be some cutoffs and approximations involved. Very often what people do then in such a non-distributive setting, they actually approximate all the data flows that happen within strongly connected components of the call graph, so that happen within recursive calls, by a flow insensitive analysis. And that's a little bit similar to what we saw in Spark, where it basically simplified the strongly connected components, because in the end, you end up with the same information everywhere within the SCC anyways, right? And so similarly here, you would have the same scenario, basically getting the same information propagated everywhere within this recursive call path. So you can just do a flow insensitive analysis for that part of the program in the first place. So it's one way to deal with this. In practice, we and also others oftentimes now try to use rather distributive problems, then you don't have these particular challenges in the first place. Another, well, not really challenge, but just something to be aware of is how to deal with parameters and return values. And here it's really good advice to map actual parameters to formal parameters and vice versa, depending on whether you are processing a call or a return. And also you shouldn't be propagating too much. So that means, for instance, by looking at that particular program here, let's assume we are doing a taint analysis starting at source, and X is being propagated to Y, and now here X and Y are tainted. Then as we are propagating information, inherited information from this call to this, method header here, basically, we are actually just propagating the formal parameter A here, right? So here we have an actual parameter X, and because X is tainted, we now know that A is tainted in this particular context here, in this scope. But in particular, we are not propagating into foo information about X, or let alone information about Y, because neither of this is relevant here. Foo doesn't even know about X. It's not even in scope within foo. only A is in scope, and therefore only this information A is being propagated here. Likewise, this can then be tainting B, but at the end, B is not returned, and neither is A, and both are local variables, so they're not in scope within main. And therefore, what we would be propagating back here is the empty set, right? So after calling foo, nothing is actually tainted here, at least not by the call to foo. Okay, and so that's what I'm trying to say. Across procedure boundaries, you should be mapping actual parameters to formal parameters when it is a call, and the other way around when it is a return edge. And you should only be propagating information that is relevant for the procedure that you're currently entering. Now, an interesting exception to that, that also I have to admit we have not yet found the perfect way to deal with, is what to do with static fields. So a static field and an access to a static field is visible anywhere in the program, right? So within foo, I could retrieve any class and any of its static fields at any point in time. They are always visible anywhere. So when let's say I'm doing something here with a field c.f, for instance, right? And then I'm calling or I'm processing the call to foo. I do not know ahead of time whether foo accesses that field c.f or not, right? Or it may even be accessed transitively by a callee of foo. I have no idea. And because I'm lacking that a priori knowledge, I can only really do one of two things. Either I can propagate information about c.f into foo, but then I would have to propagate it anywhere, everywhere in the program, because I nowhere know what is being accessed and what isn't, at least not ahead of time. Or I don't propagate it into here, but then my analysis might actually be incorrect. It might be unsound because it might be missing information about c.f, for instance, being tainted. Okay, and so we and others have been dealing with this in different ways. So, for instance, one possible way is you could do a very simple pre-analysis of the program, trying to figure out what are methods that can access static fields at all and which ones may they access. And then you can use that to filter at every call edge what information is being propagated. That's one possibility. Another possibility is to also handle assignments to and from static fields, especially in a flow insensitive manner. That might also make sense. But all of this is not very elegant, and unfortunately, we haven't found the perfect solution to this yet. So we also don't know what is optimally from an empirical point of view, right? So what gives you the best performance precision trade-off? So if any of you is still looking for a good master thesis topic, for instance, that might be one, and feel free to contact me about that. Then another problem is, or another challenge, I should say, we don't have any problems, right? We only solve challenges. So another challenge is dealing with aliasing, as so often. But here in particular, I want to point out that aliasing or aliases might be created both by the caller, but also by the callee. So for instance, if you ignore foo for a moment and only look at main and think about analyzing main, then you might think that, you know, A and B, they are basically local variables, and you pass them to foo, where they are also local variables only. So it might be sufficient to do an alias analysis just intra-procedurally for main in order to obtain a sound analysis. But as the example shows, that is not really the case, because if you only analyze within main, then you cannot know that y.f here is actually assigned x.f, and therefore in this calling context, b.f is actually being assigned a.f, and therefore b.f.g is actually the same as a.f.g up here, and therefore the source can actually leak to this leak method here. Okay, So you have to really conduct an inter-procedural alias analysis considering foo as a callee and its effects within main in order to figure that out. And that's important. And sometimes when I still see papers by people doing, interprocedural analysis maybe for the first time, not thinking about this, that's still a common mistake to make. Then another challenge is virtual dispatch. So I already explained virtual dispatch means multiple possible call targets per call site in general. Normally that's not such a big challenge, right? So if a call graph names us a number of different call targets for a given call site, the analysis would simply analyze all of them, right? So for instance, if I have a call to a interface method collection.add, let's say, and I could have multiple concrete collection types there, then I will simply assume a number of different outgoing call edges to a number of different add methods, and I'm analyzing all of them. But the question is then, if you have such possible call targets and they somehow must be considered all simultaneously, what does it really mean? In particular, you must then know, are you talking about a may or a must analysis? Because let's say you're doing a may analysis, then it's rather simple, right? So let's say I'm trying to determine whether, I don't know, a certain taint may leak somewhere. And you're looking at a number of different potential call targets, then, well, the data may leak if any of the potential callees leaks it, right? So that's rather simple. But now let's say we're doing a must analysis. So we only want to issue a warning if there is a data leak for sure. If we know without any doubt at all that this data will be leaked. Now it's different, right? So if you have different, multiple different call sites at multiple different callees, at the same call site, then we only know for sure that the data will be leaked if all the potential callees leak it, right? So now all of a sudden you have an all quantification, and that can make the analysis more complicated, right? Because now you actually have to reason about all the calls at the same time. You at the very least have to use different merge operators, right? So you might need to use intersection where you previously used union and so on. So this needs some thinking. But in general, the treatment is actually quite similar to the case of intra-procedural branches. So in the intra-procedural case, you can have an if-then-else branch, right? You can have conditional go-tos on Gimple, on the Gimple level, for instance, or you could have a switch case. So also in these cases, if you have a must analysis, like I said, you need to use intersection, for instance, rather than union. And similarly here, you can think of a virtual method call basically as an inter-procedural branch, right? So it's basically between procedures saying, well, if my runtime type is this, then I'm calling this procedure. If my runtime type is that, then I'm calling that procedure, right? And so you can think of it as a big if then else. And so the treatment at these call sites, at these virtual call sites, must be typically very similar to any treatment that you would have in these inter-procedural branching constructs. Another question that also many students always ask me is, okay, Professor Bodden, so how does this actually work on programs that are multi-threaded, right? So many programs these days, they do have multiple threads. If you think about an Android app, for instance, it's multi-threaded all the time. It's entirely event-driven. Similarly, if you now program, let's say, a serverless application or so, and yeah, then my answer is basically it depends. So first of all, it depends on your analysis scope. So if you're only analyzing part of this program, so for instance, a part that is only running in a single thread, and the rest of the program may be running in another thread, then it's not important, right? Then you can just use any kind of analysis. And similarly, in particular, that's a special case, I would say, if you're doing intra-procedural analysis, so within a single method, then that is typically sound despite any multi-threaded execution, because any single method or any single method execution that runs within a single thread, right? And it's independent of any other method execution that might be running in another thread. But if you now do inter-procedural analysis, that is typically unsound when it's flow sensitive. And that's an important condition. So if you think about a flow insensitive analysis, okay, let's say Spark, for instance, right, that does a flow insensitive pointer analysis, then that's okay to also do for a multi-threaded program. Because in a flow insensitive analysis, execution order does not matter, right? By definition, because the analysis is flow insensitive, we don't care when a certain statement executes, and so we also don't care whether it executes in another thread. So flow insensitive analysis are not impacted by multi-threading, but flow sensitive analysis are, because by their definition, flow sensitive analysis considers program ordering, right? And right now, by what I've explained so far, program ordering is encoded through an interprocedural control flow graph. And we assume that this ICFG encodes the program ordering completely, right? So if there is an edge between two nodes in an ICFG, we know that basically the successor node can only follow this predecessor node, right? Or any other predecessors that you have encoded in this very graph. But if you then have a multi-threaded program, that might not be the case anymore. And that gets then particularly interesting if you have multiple threads accessing the same data, as you can find out through an alias analysis, because then you can have data races, and then your analysis must really be aware of what can execute in parallel with which other parts of the program. And that's not simple to model at all. So I would say the effective modeling of synchronization constructs is a big open research problem. There are a few research groups I know around the world who have dedicated a lot of work to this problem. So for instance, there's one at KIT, Karlsruhe University of Technology, or Karlsruhe Institute of Technology, that's working on this by Gregor Snelting. But there is not a lot of research in this space in general. And so just suffice it to say maybe for now that if you are applying an interprocedural flow-sensitive analysis to a multi-threaded program, it can give you some unsoundness. Often from my practical experience, I would say it's not too bad. So we have certainly seen incorrect results by static analysis, in particular also false positives by static analysis, but typically not because of multi-threading. So the problem exists, but I would say it's practical, well, turnout, right? So it's the practical problem that it's really generating that's not too large, but still you should be aware of that problem. And for instance, when we analyze Android apps or so, there is a lot of multi-threading involved, like I said, but typically the kind of bugs that we are searching for with static analysis, they don't really depend on multi-threaded execution or single-threaded execution. So in these situations, it's often an orthogonal problem. Another challenge are so-called library functions. So in Java, for instance, you can typically analyze an application including the JDK, right? So you can, if you want to, analyze the program code, including the entire Java runtime library. And for Android, you can do that including the entire Android framework. It's expensive, but you can do it. But then the next question is, what about native code, right? So at the very least, this is typically where your analysis ends. So sometimes you have natively implemented methods, like they're implemented in C often and then compiled into native binary code. And then if you have a Java-based static analysis, it can't really know anything about that native code. And then the question is, how do you deal with this? So often we and also others deal by this in a very crude way using so-called handcrafted summaries. So we as experts sit down and look at the native methods that are relevant to analyzing a given program, and you can trace actually which native methods are called by that program transitively. Um, and then these methods are being modeled by hand. And so we explicitly tell the analysis, for instance, if you see a call to thread.start, it will implicitly cause a call to thread.run or to the run method of a given runnable, so that we actually explicitly model the appropriate call edges in the call graph that we use. A possible way out of this is to actually pre-compute summaries. So in our ICSI paper on StubDroid, we have done this for Android. So here we pre-computed summaries automatically for the Android runtime library, but for the Java part only actually of the Android library, so that these summaries could then be used when analyzing Android applications. The benefit there is that you don't have to reanalyze the Android library over and over again. As you're analyzing multiple apps, you only need to analyze it once. Now, you could do something similar, and that has in fact been proposed also for Android, in terms of analyzing native code or its C implementation first, extracting some summaries from there, and then using these during the analysis of the Java-based Android code. A similar challenge is a feature called reflection. So the reflection API exists in Java, but it also exists in many other current programming languages. And reflection API is basically a native API, but it's a very special one because it can be used to call any given method in the program just by its name. And this name can even be dynamically computed. So for instance, what you see here, it's a very simple program. It opens some connection, then it writes to the connection. And what you normally don't want is that you're writing to a closed connection. But here again, it's a contrived example, but basically using these reflective calls here, we're actually calling this do evil method here using reflection, and that will then close the connection so that when you write here, you have this connection in an invalid state. The problem is now if a program analysis looks at these methods, it sees a call to for name, it sees a call to get method, it sees a call to invoke, it sees no call to do evil. So it needs some special handling to interpret what's going on here. How does this reflection API actually work? And again, through some special casing, it's entirely possible to tell a static analysis how to deal with such reflective calls. So we have an implementation in Suite, in fact, that could tell you that this class here, it's not just any class, but looking at the string, it's the class evil. And therefore, this method that is being called here, it's not just any method, but it's actually this do evil method here. Okay, so this is doable, but you can have programs where this string here or that string, where they are not constant, where they're actually being computed at runtime. And in the most crude case, for instance, this method name here, it could just be a runtime argument, right? So you wouldn't know anything about the string at all. And then, of course, any static analysis of this is hopeless, right? So then you can only do one of two approximations. You can either assume that this invoke doesn't go anywhere, that might be unsound, or you can assume that it can go everywhere, or at least everywhere within that class, and that might be imprecise. And there are practical solutions to that challenge. For instance, you can do dynamic runtime tracing to actually execute this program and to see at runtime what strings it's actually loading here and what classes it's calling. We have implemented such an approach. It's called Tamiflex for taming reflection. And I'll be telling you more about this in DECA II in the next term. Now that brings me to the conclusion of this week's lecture already. So just to recap from today, we talked about context sensitivity and how it's meant to analyze a method multiple times, once per context. And that's basically essential to guarantee that the analysis only runs along realizable paths. Also, I talked about a number of practical challenges such as recursion, parameters, aliasing, and so forth. Now, in the next week, we will be going deeper into context sensitivity. I will start talking about these conceptual frameworks that I mentioned. In particular, the first framework that I will cover is the so-called call strings approach. And I'll be explaining to you how that works and what its advantages and disadvantages are. And then later in the week after, we'll be starting to talk about the functional approach, which comes in a number of different varieties, let's say. And we'll also be talking about the trade-offs that are involved there. Until then, I wish you a good rest of the week, and I'll see you back then. Bye-bye.